So much of what we predict is not a number. It's a yes or a no. Will this customer buy or not? Is this email spam or not? Every answer is one of two classes. But the straight line we learned for regression predicts any real number at all. -3, 0.710. Here's the trouble. We labeled every point 0 for no, or 1 for yes, and we want an answer living between 0 and 1, a probability. Fit a straight line though, and watch it spill straight out the top and bottom. It happily predicts 1.4 or minus zero point .3. Numbers that mean nothing as a probability. A line is the wrong shape. We need to squash it into the strip between 0 and 1. Meet the hero of this lesson, the sigmoid function, also called the logistic function. Sigma of z equals 1 over 1 plus e2, the minus z. Let me draw it, because its shape is the whole idea. Draw z along the bottom, running from far negative to far positive, and sigma of z up the side. Out comes this beautiful S, smooth, always climbing, and forever trapped between 0 and 1. Push z far to the right, e to the minus z melts to 0, and sigma flattens toward 1, a confident yes. Push z far to the left, and it hugs 0 instead, a confident no. The curve never touches either wall, it just gets ever closer. And the single most important point sits dead center. At z equals 0, e to the 0 is 1. So sigma is 1 over 1 plus 1, exactly 1/2. The curve crosses the halfway line right at the origin. Hold on to that. Sigma of 0 is 0.5. Now we build the model in two clean stages. First, take your features x, weight them, and add a bias. That's exactly the linear score from regression. Call it z. It can be any real number. Then pass that score through the sigmoid. The output, p, is our predicted probability that the answer is yes, that the class is 1. A straight line score, squashed into a probability. That is logistic regression, start to finish. And because probabilities must add to 1, the chance of the other class, class 0, is simply 1 minus p. Two numbers that always sum to a whole. A probability is lovely, but sometimes you must commit to an answer. So we threshold. The usual rule, if p is at least 1/2, call it class 1. Otherwise, class 0. Here's the neat part. We just saw sigma hits 1/2 exactly when z is 0. So thresholding the probability at 0.5 is the very same thing as thresholding the raw score z at 0, which hands us the two rules side by side. Class 1 when z is at least 0, class 0 when z is below it. The boundary between them is simply where z equals 0, and that is what we chase next. So why is it called regression at all, if it classifies? The answer is hidden one step underneath the probability. Let's follow the chain. Probability. Two odds. Two log odds. The odds of yes are p over 1 minus p. How much more likely yes is than no. And the log odds, or logit, is just the natural logarithm of that ratio. Now put p equals sigma of z into that ratio, and the algebra is gorgeous. P over 1 minus p collapses to e to the z. Take the log, and the exponential and the logarithm cancel. The log odds is simply z. And there it is. The log odds of yes equals w dot x plus b, a plain, straight line in the features. Logistic regression is a linear model, not on the probability, but on the log odds of the outcome. That transformed linearity is exactly where the word regression comes from. Let's leave one feature behind and picture two. So the whole thing lives on a plane. Each point is one example, plotted by its two features. Gold points are the yes class, blue points the no class. The boundary is the set of points where the model is perfectly undecided, where p is 1/2, which means z equals 0. Set w dot x plus b to 0. And because z is linear in the features, That equation draws a perfectly straight line across the plane. One side of that line z is positive. So the model says class 1. The other side z is negative, class 0. The line cleanly splits the plane in two. So remember this. Logistic regression always carves a straight boundary. For a curved one, you must engineer curved features first. How do we train it? How do we choose the weights? Not with squared error. We use the log laws, also called cross entropy. For one example, it reads minus, in brackets, y times log p plus 1 minus y times log 1 minus p. It looks busy, but the label switches half of it off. When the true answer is 1, only the first term survives. The loss is minus log p. When the truth is 0, only the second, minus log 1 minus p. One term always. Picture the y equals 1 case, minus log p, against the probability we predicted. Predict p near 1, the truth, and the cost sinks to 0. But predict p near 0 while the answer was really 1, and the cost rockets up toward infinity. Confident and wrong is punished savagely. And here's the deep reason we avoid squared error. Wrapped around the sigmoid, squared error is non-convex, a bumpy landscape where gradient descent can stall in a local dip. Log laws, by contrast, is convex, a single smooth valley with one global minimum. There is no neat closed form here, so we slide down that valley with gradient descent, and we always reach the bottom. Let's put real numbers through it. One feature, weight 0.5, bias minus 1. So the score is z equals 0.5x minus 1. Take the point x equals 4. First, the score 0.5 times 4 is 2 minus 1 gives z equals 1. Now the probability? Sigma of 1 is 1 over 1 plus e to the minus 1. E to the minus 1 is about 0.368. So we get 1 over 1.368. Work it out. About 0.731. So the model says roughly a 73% chance of yes. Is that class 1 or class 0? 0.731 is comfortably above 1 half. So we predict class 1. And let's verify the whole idea. The odds are p over 1 minus p, which is exactly e to the 1, 2.718, and its log is 1, rz, precisely as promised. Now two features to see a real misclassification. Let the score be x1 minus 2x2 plus 0.5. Take the point 0, 1, whose true answer is actually yes. The score is 0 minus 2 plus 0.5 minus 1.5. Sigma of minus 1.5 is 1 over 1 plus e to the 1.5, about 0.182. That's below 1 half. So the model predicts class 0, but the truth was 1. A genuine mistake. Feel what the loss does with that. The true label is 1. So the loss is minus log of 0.182, about 1.7. A hefty penalty for being wrong and fairly sure of it. Had the model instead said 0.9, close to the truth, the loss would be minus log of 0.9, only about 0.1. That gap is log loss doing its job. Your turn. Same one-feature model, z equals 0.5x minus 1. What probability does it give at x equals 2? And which class? Pause the video, work it out, and I'll wait, right here. Here's the walkthrough. 0.5 times 2 is 1, minus 1, so z is exactly 0. And sigma of 0, we know cold, is 1 half. So the probability is 0.5, which means this point sits precisely on the decision boundary. The model is perfectly torn, 50-50. By our Atlas rule, it tips to class 1, but it's the most uncertain call it can make. If you found 0.5, you've truly got the sigmoid. Trap 1. The name misleads. Logistic regression is a classifier. It models a probability and the log odds, never y itself as some raw real number. Trap 2. Confusing the two shapes. The sigmoid is a curvy S in the score z, But the decision boundary out in feature space is dead straight. Curvy squashing. Straight boundary. Trap 3. Forgetting the core output is P, a probability. The class label only appears once you threshold it, and you can tune that threshold away from one half when the costs are lopsided. And trap 4, reaching for squared error. On the sigmoid, it's non-convex and shaky to optimize. For logistic regression, always train with cross-entropy, the log laws. Let's lock it all in. Logistic regression takes a linear score and squashes it through the sigmoid into a probability P. Underneath, it's a linear model on the log odds of yes. That transformed straight line is the regression in the name. Threshold the probability at one half. Equivalently, the score at 0. And you get a class split by a perfectly straight decision boundary. And we train it with cross-entropy, the log laws, convex, and merciless on confident mistakes. Squash the line, read the probability, draw the line. That's logistic regression.